Fantastic. So welcome everybody. It's great to be here. So I'm Raoul, I'm here with Richard, and we're going to talk about collections, The Force Awakens.
Boom. Excellent.
Boom.
So collections are one of those things that stores lots of different elements, and sometimes those elements can look very similar to each other, right? Just like these stormtroopers.
There will be many Star Wars references in this talk, so hopefully everyone is a big fan of Star Wars here. But yeah, Richard, the stormtroopers, they're everywhere, just like collections. We see them every day in Java applications, but how can we improve them? What problems are there with collections? So here's our top three favorite bugs with collection. The first one is responsible for this poor all-terrain machine here, the good old-fashioned array out-of-bound exception, and typically due to accessing an element with a wrong index. Or maybe the machine drank a little bit too much. We're not quite sure here. So everyone is familiar with this exception, but there's another two interesting bugs, the concurrent modification and the check then act, which we'd like to shed some light on. So to do that, let's look at some real code. So Richard, what have we got going on here with this code?
Well, we've got a list of string with a Luke and a Yoda. So two names. The question is, are they real Jedis? And the test for our Jedi is whether their name begins with a lowercase character. And what we're going to do is, with this code, is remove from the list anyone who's a Jedi and see what happens. Yep.
Fantastic. That looks like some great code. So let's just run it, see what happens. Boom.
Concurrent modification exception. So it's a bit of a weird name, isn't it? Because concurrent modification exception sounds like there's some big concurrency thing going on. But actually, concurrent modification really normally means you're looping over something and then you try and add or remove an element.
So the problem we have going on here is this for each loop here under the hood uses an iterator object. And this iterator object is responsible for tracking the iteration of these collections of Jedis. So it needs to be able to track an index or a cursor to understand what position of the elements of the collection it's currently in. Unfortunately, what we're doing here is to remove the Jedi by directly accessing the source of those objects. So we have two objects that are sort of fighting to sync up or not sync up the elements in this stream here. So just to shed some light on what's going on under the hood, we could have written this code by using a good old-fashioned iterator object.
Vintage Java.
Vintage Java. We all love vintage Java. So what we're doing here is to use an iterator object to find out what's the next element in the collection, but by making that explicit. So what we like to do is to check that this Jedi is actually a Jedi, and if it is, then if it's not, we'll remove it from the source. However, instead of directly modifying the source, which the iterator has access to, we'll use the iterator object itself, which is responsible for the iteration and manage the state of the iterator. So we'll call remove, which is called on the iterator instead of the collection itself. So let's just run this code, and we'll see that actually we don't have a concurrent modification exception now because we're managing the iteration using the iterator object directly.
And we got rid of Yoda.
Poor little Yoda.
Poor little Yoda.
Richard, do you like this code? To me, it looks really verbose.
Well, when we had the for each loop, it was a lot more sugared, it was a lot more nice, a lot more friendly. But in Java 8, isn't there a nice little method that's been added that perhaps gives us the readability benefits of one kind of approach and also the safety of the other?
Yes. And this method, Richard and I, we are big fans of Java 8. And this method here, remove if, takes a predicate as an argument, which is the test for whether we have a Jedi or not, and will mutate the source collection to remove the element if the predicate evaluates to true. So let's just run this code, and we can see we get the expected output, and it's a lot friendlier, less verbose, and less error prone as well. So we win on two fronts.
Reads more like the problem statement as well. Jedi's remove if, and then the first character of their name's lowercase.
Exactly. So, Richard, let's maybe jump to another example, another really interesting kind of problem, the check then act pattern. Great for dinner parties.
Fantastic. Check then act. So you've got a Phantom Menace related example here, Raoul? Are you trying to just insult all the viewers? What's going on?
As we all know, the Phantom Menace was a great, great movie, Richard. Come on. And because it was that great, we're just going to watch it lots of times. That's what we're going to do here. So we've got a little bit of piece of code here that basically stores a count for different movies that we may be watching. So maybe we're creating a new app to beat Netflix, and the only movie we want to watch is The Phantom Menace. So we're just going to initialize this map. And we've got some little code here that's basically sequentially going to increment the number of views for the movies, pretending that, you know, different viewers are watching this movie one after the other one. So this is some very, very simple code for the purpose of the example. We, you know, iterate through a counter of 100,000 views, and we're just going to add one view to this map. And to do that, we do what we call the check then act pattern. So we look up the number of views in the map for this movie. We check that it's been initialized, and if it's been initialized, then we update this value by adding 1 to it. Fantastic. So let's just run this code and see what kind of output we're going to get. Fantastic, Richard. Looks like the code is working repeatedly.
100,000 Phantom Menace views. Raoul's code works, but his movie taste is questionable. That's the takeaway from this live coding. So what else? I see you've got a concurrent add method going on there, Raoul. What happens if you run the concurrent add method?
So Richard, I think we need to go web scale. As we know, we've got lots of big data here, so let's go web scale.
Amazing.
So let's use 2 threads. Let's use a thread pool here with 2 threads. And instead of doing a sequential add, we'll do a concurrent add. What the concurrent add is going to do is to leverage this thread pool that we created and send jobs to it. And the jobs are essentially to increment this this movie catalog and increment the number of views. Okay. So let's run this code.
So what you're saying is each of those things, instead of being run in just a plain old loop, we're going to submit a job to the thread pool that says run that add 1 view. And because we've got 2 threads in the thread pool, they're going to be going on at the same time or overlapping in some sense.
Precisely. So let's run this code. Nightmare. I mean, Richard, you must be happy here because we watched the movie less than 100 times, 100,000 times.
Wow. So you've thrown away data. I mean, in this case, it's people watching The Phantom Menace, so it's actually not that bad a thing that there's no record of it. But if it was a good film, this could be really bad. This
would be really bad. So what we've got going on here is, since we've got this add 1 view method here, this add 1 view method here is not atomic. It's made out of different steps. The first is looking up, then is checking that the map is initialized, and only after that we are updating the value. So our threads here could be interrupted at any of those different steps and overriding one another results. So that's what we have going on here. We have a big fat
hold on a minute, Raoul. I've heard Java's got a concurrent hash map. Can't we just prefix the collection name with concurrent and then it just works?
That's an excellent idea, Richard. Let's go for concurrent hash map. Must be working.
Yeah, it's got concurrent in the name.
And still doesn't work, unfortunately.
Throwing away even more views in some cases here. Wow. Wow.
Completely undeterministic.
So does that mean the concurrent hash map is broken?
Well, I suspect that the concurrent hash map is not broken because lots and lots of research and work has been put into this data structure. So maybe the problem, Richard, is our code, right? How we actually using the concurrent hash map.
Realistically, the bug's more likely to be in our code than in the concurrent hash map implementation.
Yes. So if we go back to this add one view method here, as we said, there's different steps going on here. One is the lookup of the count from the movies, the number of views. Then we're checking whether that has been initialized, and if it has, we only at that point will actually add will increment the number of views. So this is a compound operation. Even though the concurrent hash map manages the synchronization of different methods internally, it's not managing the synchronization of this compound operation for us, and this is where the bug relies. So Richard, let's use some vintage Java again here.
Okay.
What we're going to try and do here is try to atomically update this concurrent hash map. And if we fail to do that, we'll try again until we manage.
Okay. So it's a bit like a database transaction in an MVCC style database where you say, hey, we'll try it. We'll see if it failed again, and then we'll try again. Or if it succeeded, we'll just finish the code and complete. Or like a compare and swap loop if you've ever done some low-level concurrency.
And the key operation to achieve that is called replace, which is available in the concurrent hash map, and that's going to take the key that we want to look up. It's going to take the expected value to find in the map. And if we see this value, only then can we actually update it with a newer value. So if that succeeds, then we can break out of this loop. If that fails, we'll try again until it works out. So it's a little bit verbose, it's a little bit ugly. So let's see if it works. Fantastic. At least it works, Richard.
Excellent. So you've run it a few times. We've got the replace going on. That's lovely. But it is, as you say, really, really verbose. And if I came along and read that code, it would be quite unclear to me what's going on. Is there anything that Java 8 provides us that helps?
Indeed. Again, we're a big fan of Java 8, and Java 8 added an atomic operation called compute if present, supported in the concurrent hash map, which lets us apply this compound operation, sort of check then add pattern using a method called compute if present. And that's going to take essentially a couple of arguments. One, which is the key, and the second one, which is a function to indicate how we'd like to update the map. So the key here is the movie. So that's the key we want to look up. And then we have the number of
views.
Here.
The function takes the key and the value, so it's gonna also have the name of the movie as a parameter passed to it.
Views, and only in that case we will update the map using this operation here, which is going to increment the counter for that movie. You can see it looks friendlier. It reads like the problem statement, but let's see if it actually works, right?
Yeah.
Fantastic. The code works. Beautiful.
Awesome. Running it a few times works deterministically. Lovely. We can ship it.
We should write a test as well before we ship it.
Nah, let's just ship it.
So, the slide here covers what we've just described. But what's interesting here is you may be thinking, hold on, guys, that looks a bit like a contrived example. Well, there's some research that looked at a few very famous and open source Java projects, including Cassandra and Lucene. And what they found is that actually 280 bugs in those projects were related to this check then act pattern in the context of concurrency. So there's an interesting story here is that as we make use of different patterns and new idioms emerges, this is where help from the library can help us write code that is more readable, but also less error prone. And we see that in Java 8 thanks to this remove if method and also this compute if present method that were added. And later on in this talk, we'll also talk about different data structures that can help us to reduce the scope for bugs. So that covers what we've been doing in vintage Java. And what we're going to look at now is
let's talk about you're breaking up a little bit. 8 and 9. Can you hear me okay?
Yes. So, Richard, the first thing, lazy collection initialization.
Lazy collections initialization, exactly. So it turns out that a lot of uses of both hash maps and array lists are never actually written to. So superficially, this might seem a bit crazy. Why would you have a hash map or array list, but you never use it? But for example, you might do something like pass in a map of the parameters to an HTTP call. But if there's no parameters to the get, then it's just an empty map. You also get this kind of null object pattern, whereby as opposed to returning null, you just return an empty collection as well, or if the return value is a collection. So what it turns out is that Java 8 adds lazy initialization for this default case. So it doesn't actually allocate the backing array in an array list or the backing array of entries in a hash map until you write the first element into, and it actually has to use it. And interestingly enough, this does both reduce allocation rates, as in the rate at which memory is allocated, which is a nice performance win, and also total memory consumption. Fantastic. Let's say it together. Optional.get. It's a trap.
It's a big trap.
It's a big trap. So this is kind of an interesting one. After the optional class was released, an observation was made that most users of optional.get were kind of misusers. They were people who weren't checking whether the optional value was present before calling .get. Obviously, if you went on a training course by Raoul and I, that wouldn't be a problem. But you know, that is a thing that people do. And one of the ongoing interesting changes is the idea that the get method will probably be deprecated. Now, it's unlikely to be deprecated in the Java 9 release due to schedule constraints, and it will be replaced with a method with a longer name, get when present, for example. With the idea that you might actually need that get as a breakout of jail card for the optional value at some point, but you should be kind of discouraged from using it most of the time. There's also a bunch of other functionality improvements added to Java ETL optional, such as if present or else or in stream, and also massive improvements to the stream and collectors API as well. If you go to iteratorlearning.com afterwards, you can see that Raoul and I have written up a series of articles showing concrete examples of where you might want to use these things. There's
also improvements added to completable future, which is another data type that was introduced in Java 8, and to provide support for asynchronous timeouts in a much friendlier way than what Java 8 currently provides as well.
Another nice little improvement that you see in Java 9 is the collection factory methods. So heavily used in Guava are those things like lists.newArrayList, like thing that give you a collection with a specific series of values, and there's some factory methods on both the and concrete classes to build them up in Java 9. So that's a nice improvement. It doesn't extend, though, to the persistent immutable collections, which we'll be talking about a little bit more in this talk later on. Like now. So we can kind of think about collections as falling into different categories. There's our regular mutable collections, like say an array list, which if you want to update, you update in place. You add an element and it goes into the list that you've got a reference to. And those could be unsynchronized, like array list, or they could be concurrent. So some kind of synchronization on that shared state, like a concurrent hash map, for example, is very, very commonly used. Then there are unmodifiable views of collections. So these aren't actually collections themselves. They're just kind of wrappers that let you read from a collection without modifying them. And that leaves you with mutable state, but you've restricted who can actually mutate that state. You've done some kind of encapsulation potentially on your data. And then there's the more functional worldview type collections, the immutable collections. And these come in non-persistent and persistent forms. So, what are those, Raoul?
Well, before we talk about the interesting functional stuff, which I think, we need to be a lot friendlier with, it would be nice to sort of review the benefits and downsides of what we're currently doing in Java, Richard.
Yes, that's true. So already we can have these existing mutable collections, as we say, a ArrayList HashMap tree set. They're pretty memory efficient. And as we say, you can have thread-safe mutable collections like concurrent HashMap, but you need to be careful in your design of them. So usually those are things that are shipped in the libraries. The unmodifiable view, as I say, is a way of restricting the mutation around a single type of collection. So here we've got a list of Jedis containing Luke Skywalker, and we wrap our unmodifiable list wrapper around this Jedis, which we call can't change me. So if you try to add Darth Vader into this list of can't change me's, that would fail with an unsupported operation exception. So you couldn't modify those things. So these are actually really useful. And there is a downside. Just like the Death Star, sometimes things that look like they've got a really strong protective wrapper around the outside have one little flaw under the hood, one little exhaust vent. And the exhaust vent in the unmodifiable collections cases, you can still modify the collection that's being wrapped. So you still have to be careful with not handing out a reference to that underlying collection and controlling who modifies it.
So we don't mean to give any spoilers here. So if you haven't seen the movie, we encourage you to watch it, and you're in for a good surprise. Fantastic. Well, that's the mutable world. That's what we are used to doing in Java. But Richard and I, we feel like the functional guys, they're getting a bad rep. We're not being nice to them as Java developers. But there is a lot of good stuff that we can learn from a functional programming. And one is the idea of immutability, specifically a data structure is immutable and non-persistent. What does that mean? Well, it means that you can't actually update your data structure. So it's a little bit like a Death Star that is, completely protected. There's nothing you can do about it. You can't change it. You can't destroy it. But the reason why those data structures are getting a really bad reputation is because, well, what if we actually want to introduce a change? What do we do? Well, the only thing we can do is to copy the whole data structure and provide an updated version of it, which can be quite expensive if you have large collections of objects. However, there's a lot of good stuff that you get with an immutable data structure. The first one is that since you're not going to change it, its underlying representation could be more efficient. For example, you could have an immutable tree represented through a normal array, which has great cache locality. The other benefit is that you don't need to synchronize the data structure because you're not going to change it. So there's no locking required in the context of concurrency. If you're a library designer and you have an interest with type system, immutable data structure provides also a covariant subtyping characteristic, which means if you have a list of master Jedis, you could use that in the context of a list of Jedis because there is a subtyping relationship between those two types. So you get more flexibility as well. So lots of good stuff. The question is, well, if immutable collections are so good, then how could we incorporate them in the Java standard library? Because, in fact, mutable and immutable are quite two different things. So is it possible to even use those two concepts together? Well, here's an example taken from the Eclipse collections. And they have a very interesting type hierarchy here, where they introduce a mutable list, which is implementing the list interface from the Java standard API here, which means you can use a mutable list in the context of a normal list, which is great. Mutable list and mutable list share a common parent interface, a list iterable, which only declares read-only methods, which means you can substitute use of an immutable list and mutable list in the context of a list iterable. So both can be used if you are promising that you're only using read-only operation through this list iterable interface.
So that's great, right? Because that means you could write code that works just on list iterable, and then it wouldn't necessarily matter which of those views you're plugging underneath as well. So that also means that you could incrementally move an application from an immutable to a mutable collection style, or vice versa, much more easily as well. Makes the adoption of these things nicer.
Precisely. But Richard, we still have this problem that those immutable collections involve a lot of copying if we want to introduce changes. And this is the next topic that we're going to talk about, is how can we have a mutable and persistent. What persistent means is that we can provide a new version of this collection. Non-persistent data structure means we don't support new versions.
Yeah. So what you're saying is, with the non-persistent versions, if I only wanted to add one element, I'd have to copy all of the previous elements across as well into the new collection you're creating. So how can we avoid that?
Well, let's learn a little bit about what the list guys have been doing for a few decades. Unfortunately, we can't see you guys, but there's always that one guy, that one person that loves Lisp. And so be great to do a high five here, but we can't see you guys. But what the Lisp programming language came up with is this idea of a const list. And this is sort of a basic Java implementation of it. We have an element, which is the head of this list, supported by a tail. And if you want to add a new element to this list, what you can do is to wrap up the current const list together with a new element. By doing this, we're not changing an existing data structure. We're just wrapping up an existing one, referencing to the tail. So that's a key technical trick here, which lets us avoid mutation. So how would it work if, instead of appending to a list, we'd like to be able to modify an existing element? So let's say we want to modify the element C here. How can we do that without having to change the existing data structure? Well, the key trick here is to realize, well, if I need to modify C, so with a new value called D, what I can do is to create a copy of that. So that's going to be the new node, and have that link back to the tail. So we're sharing some information with the previous version of this data structure. But since we've introduced this new element called D, how can I get B to link back to it? Well, since we can't mutate the node B, then we're going to have to create a copy of it. And unfortunately, the element A here is also pointing to B. We can't modify that. So what we can do is to copy it and have the new copy point to the new copy of B. So the only thing we need to do here is, if we want to update an element, is to copy all the previous elements and having that link back to the remaining of the list. So we don't have to copy everything. We only need to copy everything leading to the element that we need to modify.
So this works really well if you want to update the element at the beginning of the list, but not so well if you want to update the element of the tail of the list, right? Because you'd have to copy everything up to that tail.
Precisely. So we'll see how we can improve this, but a similar strategy can be used if you like to concatenate to list, for example, here. What we need to do is to just copy the first part of the list and link that back to the second part of the list. And there's a few downsides. The one that you mentioned, Richard, is, yeah, it doesn't really work out very well if the lists have different sizes, or if we want to modify an element at the end of the list. And also, all those pointers lead to a poor locality. So let's see how we can improve this a little bit. Well, the first trick to realize is one thing we could improve is the iteration. Instead of having to iterate through all those nodes and having poor locality, maybe we can improve the lookup access a little bit. The second thing that we could improve here is the data decomposition property. Because we have to iterate through this whole list, it's really difficult to split up this data if we'd like to be able to provide different shards to be executed in parallel. So there's another data structure called the binary tree, which lets us improve a little bit the lookup access. And the idea here is that instead of having a flattened list, we can sort of subdivide the elements a little bit based on whether the nodes can be compared. And that let us have us a data structure here that has fewer nestings. So we've got a tree here, which has 7 elements. But if we like to fetch this node here at the bottom right, we only need to do 2 access to get to it. So if we like to modify this element, again, what we need to do is to copy all the nodes leading to it and link those back to the first version of the data structure. So we don't have to copy 8 elements here, we only need to copy 3 of them. So that's an interesting win that we're getting here. We can reduce the number of copies by using a different data structure.
But there's still quite a lot of pointer indirection with that approach, right?
Indeed. So in an ideal world, we'd like to get the power of both the Jedis and the Sith. So we like to get the performance of a mutable data structure, something like an array. But we also like to get the safety properties that the immutable data structure provides us.
Awesome. Best of both worlds.
Best of both worlds. And there's been some recent advancements in data structure that lets us do that. And the first one is what we call a trie. And the general intuition with a trie is that you take your binary tree, but instead of having a binary tree, you can have an arbitrary branching factor. So you can have a root can have many children. The other intuition is that all the data is actually only available at the leaf nodes. And to look up a leaf node, you have to traverse all the edges leading to that leaf node. So this example here, a trie is very useful, for example, to store a dictionary, and you want to look up words given a prefix. Then I could look up all the words starting with the prefix AB. So I would navigate through the edges, and then the leaf node will tell me that we have 10 words that starts with the prefix AB. So trie really useful for those kinds of problems. So how can we apply this to solve a problem with a tree example? Well, a new data structure called a bitmap vector trie use this general idea that you can have a larger branching factor than a binary tree. And if we use a larger branching factor, that means we'll reduce the number of lookups required to find the specific element that we like to update. So the index of the array, it's going to be translated into a bit representation. And this bit representation here lets us look up the appropriate children's in this tree until we find the leaf node that we wish to update. For example, if we have a branching factor of 32, we could store up to 33 million elements, so 32 to the power 5. And that would give us a tree with a depth of only 5.
Big data.
Big data. So if we need to find and update an element in this data structure, we only need to do 5 lookups. If we were using a binary tree, we would have to do significantly more lookups. So that's a key enhancement to existing data structure, is this idea of a persistent array to a bitmap vector trie. You can use a branching factor that is larger than 2, and that will reduce the number of lookups that you need to do. In this case, only 5 to store many elements. But like everything, there's a little bit of a trade-off. having a large branching factor facilitate iteration. We only need to do 5 lookups to find any elements. But it really hinders updates because at every level we have 32 elements that we need to copy every time. So there's still a number of copying required. But if we use a small branching factor, then we need to do less copying because there's fewer elements that we need to copy. However, it really hinders the traversal because the depth of the tree becomes larger. And to locate a specific element, we need to traverse this whole tree. So that's the trade-off. But so the magic numbers that different implementation of this bitmap vector trie use is 32. That lets you store a significant number of elements and also provides a good trade-off between iteration and copying required. So there's different implementations of persistent collections available in Java. Existing projects include P collections. There's different ports from Clojure and Scala available in Java if you like to use them. And also Java Slang has added recent support for those persistent collections.
I've been keeping an eye on the pull requests for the Java Slang stuff, and actually they've not actually integrated it yet, but their implementation is looking very, very performant, and they've done a lot of work on optimizing and tuning the Java Slang implementation. So I think once they merge it, it could be a great contender.
But Richard, how does that compare to existing data structures that we're using in Java?
Yeah, so it's interesting. One of the things that we often have a look at when we're talking about the overhead of persistent data structures is not just the computational cost. There's potentially a lot of memory cost. This is traditionally really bad when you see a kind of linked list type structure, a lot of overhead and all the pointers to do point chasing. But actually, as Raoul was doing, he did a quick benchmark here with Java Object Layout Project, which is actually a really good tool if you want to see, hey, how much memory does this class or this data structure actually eat up? And obviously, if you're trying to store some integer values, the best way memory consumption-wise is the primitive int array. Obviously, if you move to the integer array, it takes up a lot more memory. And it would vary as well, depending upon whether you're in a 32-bit or 64-bit architecture. Array lists of integer, of course, tend to take up a little bit more memory again than the box integer array, because they double in size periodically. And it turns out that a lot of sizes you look at, you actually end up using more memory with the array list version than the trie version, because you have to double this array list in size periodically. So you end up with a lot of slots which are actually not used by values themselves, which is quite interesting. The other thing to remember is that in a future version of Java, hopefully, you'll be able to do an array list of primitive int, which would massively improve the array list situation. But at the moment, it's not necessarily that bad. You can also, even before this Java 10 and beyond type Project Valhalla primitive specialized generics that lets you do an array list of primitive int, you can already do primitive specialized collections today. So Java 8, just in the core libraries, added primitive specialized stream operations when it added stream operations. So there's an int stream, a long stream, and a double stream that are primitive variants of the generic stream API. And to go along with them, there are primitive specialized functional interfaces as well. If you want concrete collections, though, the Java core library does not provide any primitive specialized collections. But there's a bunch of third-party libraries that do. I've contributed loads to the Urma library, which is used in things like the Aero project. There's also Warburton, Eclipse collections that provide. Eclipse collections explicitly provides a lot more functionality as well as primitive specialized collections. And hopefully Valhalla will come along one day to provide a nice generic solution. So I think the key takeaways from this section is that immutability really does reduce the scope for bugs. And being able to extend this to the collections side of things is very useful, because collections are really commonly used in Java applications. there's always this compromise and trade-off between safety and performance, but the performance of persistent data structures is improving and may well be a suitable one for use case even today.
So we're now approaching the final section of our talk, which we'll briefly cover. So we'd like to talk about a hash map, and for that we need to call our good old friend Yoda here. Map hash. So quickly covering some very basics about hash maps. So classic data structure that lets you store a key and associate that to a value. So let's say we've got a Han Solo here, a hash map. Classic implementation is backed up by an array. So we need to be able to associate an index to this key. And to do that, we have what we call a hash code, which will produce an index so we can inject the key and the value here in the appropriate slot in the array. But unfortunately, Han Solo has a very good friend called Chewbacca. And if Chewbacca as a key produce the same hash, then suddenly we'll have Han Solo and the respective value, and Chewbacca with its respective value stored in the same slot. So which value should we actually provide back? And that's typically what we call a collision between two keys. So we need a way to be able to resolve those collisions. There are two approaches available to resolve collisions. One is called chaining, where the hash map will have an underlying data structure here to be able to resolve and look up collisions. Another one called probing, where you store all the elements in line and you have a sequence to be able to identify what's the actual element that you like to be able to return. So like with everything, when you talk about algorithms, data structures, there's always different names, and we're seeing that in Star Wars as well. You've got Palpatine, which is the sort of the evil-friendly version of the Emperor, but has an alias, which is a Darth Sidious. So two names for exactly the same evil person. And we're seeing that as well with hash maps and the collision resolution approaches. So chaining is often referred to as close addressing, but also open hashing. And
yeah, not only picked different names, but different names that sound very, very similar.
Yeah, probing is called open addressing to make it more confusing, and also closed hashing, so really confusing. What we're going to focus on now is to talk about the chaining, specifically two approaches. One using linked list approach, which is something that was used before Java 8. And then maybe the sort of new approach using a tree-based approach. So Richard, what are the different trade-offs for using a linked list approach to resolve collision or a tree-based approach?
Well, it's interesting because Java util hash map traditionally did this linked list approach. And the problem with the linked list approach is if you have a very, very high collision rate, then the performance approaches order n lookup speed. Because you end up just chaining through the linked list and all the elements end up in your linked list. But if you move to a tree-based approach, you end up using a lot more memory because tree nodes have to point to both their left and right leaves as well. So in Java, HashMap and Java 8 onwards starts off to use this list, this linked list for storing the colliding values. And then when it's got over 8 elements, which is some magic number determined by one hopes benchmarking, then it switches to a tree-based implementation. So it uses more memory, but what that means is if you get heavy collisions, you end up in an order log n lookup rather than order n lookup. Now, in order to have a way of determining the tree structure, how to enter things into the tree, you need to have comparable keys. So this is something that only works if you have comparable keys. But conveniently, a lot of keys for hash maps are numbers, strings, things like that that have comparable order anyway. So,
Richard, we need a winner.
We need a winner. We need a winner. You're right. Which hash map's best? So we've had to play around with a few different approaches here and built up a little performance model of the different trade-offs that you get from benchmarking collections. So what I see when you look at a lot of benchmarks online is that what I would call a jar jar benchmark. Okay. And I call those things a Jar Jar benchmark because it's a bit like Jar Jar Binks, i.e. completely useless in any situation whatsoever. You've got to kind of explore different models and factors of things that underline the performance. So what are those kind of different factors? Firstly, the load factor, like how full is the hash map in question? Secondly, you've got to look at the kind of key access. Some people access keys linearly, like you'll end up with the pattern of access being the order in which things are inserted in the hash map. Sometimes not. Sometimes people make assumptions around that. Your get method could return or not return a value associated with it. So there are two different cases to benchmark there. So things like collision rates. Is your key comparable or not? Does it have those optimizations available or not? All sorts of different things that you need to look at. One particularly interesting case which we had a look at was, does this tree optimization work effectively? Well, what you can see here is the average insertion time for a hash map which has a comparable or incomparable key. And obviously, for comparable keys, we're using the tree map optimization. For incomparable keys, we don't get the tree map optimizations as an effect at all. So this benchmark demonstrates that if you have a very high collision rate, you end up seeing a much significant reduction in the cost of operations. But if we drop the collision rate down to 10%, where it's very low, it actually doesn't impact things very much. So even though it's quite an interesting change that's happened in Java 8, it's really only useful if you've got both comparable keys and also high collision rates. Another question people often ask is, which is better, probing or chaining? Well, probing maps often win on the memory consumption front as well. And in small maps, probing never ends up with these long clusters. So the problem with probing is you have a long cluster of things that collide. You end up linearly probing down the whole map, and it gets very, very slow eventually. Approximates, one of those rank cases again as well. So probing, you can often get a win with small hash maps, but sadly, as hash maps get bigger and as you end up with really bad collision rates, chaining often wins out. So there's no real clear-cut winner between the two. JDK implementations are, or the hash map implementation of JDK at least, is chaining based. So it tries to minimize the worst case of having high collision rates. A lot of hash code implementations are very bad, and this often causes a very poor performance with a probing-based implementation. So that's why the minimizing worst-case scenario is picked. If you do have a hash code based upon identity, you can also use the identity hash map in the JDK, which conveniently uses a linear probing approach because identity hash codes are very well distributed. So, in conclusion, we also had a quick look at some of the interface popularity. So an interesting takeaway here was, even though navigable sets and navigable maps, everything that implements a sorted set and a sorted map in JDK also implements a navigable set and navigable map. And they have additional functionality, people rarely use them. So this is based upon a corpus analysis of source code in the Debian open source project. Raoul, what happens with implementations?
Well, we can see here that a hash map is very popular now. But we can also see that things like you mentioned, like an identity hash map, something that could be useful in use case if you just want to do the lookup based on identity. It is not actually used very much, but would actually perform better in the case that you're happy with this requirement. So often some data structure are not as known as others. The thing worth mentioning here is that, we've come a long way since collections were added to Java 1.2. Evolutions can be interesting. Now we're saying that we've got a stream API, we've got different idioms. They're making it as a built-in method to let us write code that is more readable and less prone for bugs. So who knows what's coming in Java 10? Well, given we've got primitive specialized generics coming as well, we'll definitely see more and more improvements in this space.
Hopefully. Yeah, so I guess there's two big areas which these improvements focus on. One of them is improving the performance side of things, and the other one is improving the safety side of things. And hopefully with things like better persistent immutable collections, you get a nice win on both of those fronts.
So we realized that we've come a little bit longer than 45 minutes, so we're quite happy to take questions. But just before that, Richard and I, we run a training organization called Iterated Learning, and we have courses on model development using Java 8, a new course on reactive and asynchronous Java if you're interested in what's going on with completable features and actors and reactive programming. And we also have a sort of software development masterclass that covers generics, testing, collections, etc. So we'll now hand over and take any questions.
So we've actually only got a few minutes to the next session. So unfortunately, we don't have any time for questions. But what I will encourage you to do actually is if you join the VJUG IRC, we have actually a really interesting discussion going on about how you can change whether you can or can't change the base collection when you have an immutable collection from that. So okay. I very much encourage you to join that IRC chat and to see what's going on there. But we've got another session just a few minutes, so we're gonna bring Lucas in at the minute. What I will say is a massive thank you to both Raoul and to Richard for another great session. There's plenty of discussion in IRC, which is always a good sign.
Excellent.
People getting a lot out of the VJUG. How is that for you guys in Melbourne?
Yeah, fantastic. Round of applause for these guys.
Awesome.
Thanks for having us, Simon.
Thanks for having us.
It's our pleasure. And I'll just say a massive thank you to Con and to the Melbourne group as well for joining us and for being awesome for the last 3 hours.